We're going to begin an exploration of functions. These are commands, or groups of commands, to get things done. They're like mini programs that take in some input, perform some action, and return some output. Use of functions also demonstrates what I consider to be the most important idea in computer science: abstraction. Now, when we talk about abstraction, here's what we mean. We simplify all the details away, and we view a complex system through a simpler interface. We say that we've abstracted away the complexity. This happens all over in programming, and in computer science in general. We've already seen abstraction when we talked early on about the three main parts of a computer: memory, processor, and input-output. The very fact that we could talk about those in such general terms is an example of abstraction. We can talk about memory as something that lets us store information, and we don't have to understand the physics of how this occurs. We don't have to understand the circuitry that makes up a processor to understand the basic commands it supports. And input-output, wow, that's a pretty complex system of operations. To get the signals from a keyboard into the computer, and to take values and determine how to light up individual pixels on the screen to display the text, well, we get to just abstract it into input and print statements. The programming language itself is another place where abstraction is extremely important. We get to describe computer commands at a very high level that people can understand, instead of those detailed instructions that the computer understands. Now, one of the main ways that we take advantage of abstraction when programming is through functions. And though you might not realize it, we've already been using functions. The print and the input commands are examples of functions. We have the name of a function, followed by parentheses, that might or might not have something inside of them. Now, the term function is not universal. Other names you'll hear are routine, subroutine, procedure, and you'll also hear method, although that's only used in the context of object-oriented programming, which is the way we'll use method ourselves later on in the course. Now, sometimes people use the term function with a more specific meaning, much closer to the mathematical definition. In that definition, a function always returns a value. So for commands like print that don't return anything, we'd have to use a different term. But people discussing Python are usually more flexible, and all these terms have pretty much the same meaning. Just recognize that when people say function, routine, subroutine, procedure, or method, they're pretty much talking about the same idea. Now, some functions, like the print function, just do something. When a program asks a function to do its thing, the term we use is calling the function. When you call the function, something happens, like text getting printed to the screen. Other functions, like the input function, not only perform some action, like printing to the screen, they also return a value. For the input function, the function returns a string. That's whatever the person typed in. This return value can get assigned to a variable or whatever else is needed. When we think of function calls, the typical way to think of them is as a black box. The function takes in some input, or not, then the function does something. We don't want to, in fact, we don't need to think about how it does what it does. Then it returns some output, or not. For the person using the function, it's a mysterious box that takes input, does its thing, and produces output. Now, consider the perspective of someone creating a function. If you're creating a function, you get input from somewhere, you do your thing, and you send your output back out. You don't really care where the input is coming from or where your output is going. If you're writing the details of how the print statement would work, you don't need to know where that string came from or why the user wanted it printed. You just need to take whatever string is passed in and figure out how to print it out to the screen. And if you're writing the input command, you don't need to know how that string is going to get used. You just need to get the string from the user and pass it along as the output. As you write the details of your code, you'll find yourself writing functions. You'll also find that within those functions, you'll make use of more function calls. Function calls are when you initiate some action that's been defined with a function. Calling print means that we're using the print function, and calling input means that we're using the input function, And you can treat these calls as black boxes of their own. You can think of this whole process like a series of layers. You don't need to worry about what's happening in the layers above you, where that input is coming from, or where the output is going. You don't need to worry about the layers below you, how all those function calls are working internally. You just need to worry about your own layer. Another way that we talk about this in programming is to describe this as managing complexity. We want to limit the complexity that we have to think about to just the concepts at the layer that we're working in. A programmer doesn't need to understand every level of complexity, at least not at the same time. Programmers only need to understand the details at the one level they're working in at the time. Writing functions to work in Python has two different stages: defining the function and then calling the function to put it into use. We've already been calling functions, so let's look now at how functions are defined. We define a function by starting with the key term def, short for define. Next, we have the name of our function, the command that we want to use to call the function. Following that are parentheses. If our function is going to take in some form of input, that information is going to be specified inside the parentheses. Then we have a colon, just like we've seen in conditionals and loops. And finally, we have the commands that the function should do. These are indented in, again, just like we saw with conditionals and loops. The term we use for that first line defining the function is called its header, and the actual commands that it should do, the part that's indented in, is called the body. Suppose we want to create a function that just processes something and doesn't take any input and doesn't return any values. Maybe it just prints a particular warning message. Notice that we start with the word def, short for definition. We then have a name for the function, in this case, warn. There's nothing inside the parentheses, since this function doesn't take any input. After the colon, we indent the commands that we want. In this case, there's just one command, a print statement that displays a warning message. Now, when we're writing code, we can actually call this function. We might have some code and in the middle of it, decide that we need to print out a warning message. We can do so by calling warn, just like we would any other command. Notice that we need to have parentheses after the name of the function. When we execute this code, it works like you were hopefully expecting it to. The code before the function call works just like always, in this case printing the value 3. Then, when we get to the function call, it executes the function, in this case printing the warning message. After that, it executes the rest of the code just like always. Now, this might seem a little silly. I mean, couldn't we have just output that warning message directly? The code you see here works exactly the same way, and we didn't have to bother creating a function to do it. So why do you think we'd want a function to do something like this? Let me illustrate one of the ways that functions can be useful. Let's say that you have some code where you're asking users for sensitive information, and you want to give them plenty of warning that they're about to do something dangerous. You might print a warning each time before you ask for information, like you see here. Well, this is a lot of repetition for the exact same thing. And when you're repeating the same commands over and over, this is often a good time to use a function. It's straightforward to convert the warning message to a function. We simply define a function, warn, that prints the warning message. Then we can replace every occurrence of the print statement with a call to warn. Notice that this code looks a whole lot cleaner. It also makes it easier to make changes that need to happen everywhere. Let's say that you wanted to change the warning message. Well, here's a different warning message. We've changed use program at your own risk to you're about to enter sensitive information. We needed to make only one change instead of hunting down every place we had the message and changing it in each of those locations. We can also easily expand our warning. Here, we've augmented our warn function further. After printing our warning, we ask whether the person wants to continue. If the answer is N for no, then we quit the program entirely. Notice that to quit, we call a function named quit. That's a function provided in Python that we haven't seen before, and it's used in cases like this where we're ready to quit the program but are buried somewhere in the middle of the code. The point here is that the use of functions has allowed us to conceptually separate a piece of functionality from the rest of the code. That is, we've been able to take some set of commands and pull them away from all the rest of the code. So, we don't have to know about the rest of the code to use those commands, and the rest of the code doesn't need to know the details of those commands. Look at that same code again, where I've inserted some comment lines to break it up visually. If you look at the top part, the warn function, notice that we can write it while being completely oblivious to where it's being called. All we have to know is that we're giving out the warning message and asking to continue or not. There's no reason we need to know anything about the code at the bottom. And likewise, for the code at the bottom, we don't need to know anything about how the warn command is working. All we need to know is that when we're ready to give out a warning, we make a call to warn. So, when should you aim to use functions? First, anytime that you find that you're doing the same task in different places in the code, it's almost always good to use a function. The warn function that we were just looking at is an example. Using a function not only means less typing, it means less of a chance that you'll have a bug, since any errors are going to appear every time instead of just once. And once you fix the bug, it's fixed everywhere that program is used. Second, anytime you have a concept that you can consider as a single unit, or a discrete idea, it's a good idea to use a function to encapsulate it. For instance, say you're writing a program to manage your home business. Let's say that you have a program that lets you enter clients. It does some other stuff to figure out how much they owe you, and then it prints a bill. You have 3 different lists, one for the names, one for the addresses, and one for the balance owed by each client. There's a loop where we collect client information, as long as there's at least one client. Then, at some point later, we loop through our client names, and for each one who has a positive balance, we print out a message about how much that person owes. In a situation like this, we would want to identify what part of the code represented a single idea and pull it out into a function. For instance, the idea of getting information about a single client seems like a discrete task that we'd do. So, we pull it out into a function called getClient. In this case, it's the exact same code we had before. We get the name and address from the user, and we append information onto the lists of client names, addresses, and balances. Where we had that code originally, we now have just a call to getClient. We've made an abstraction here. We have the concept of getting client information. So, in our main code, when it's time to get client info, we don't worry about the details. We just call getClient. And our getClient routine doesn't worry about when it's called, it just does its own thing. We could do the same thing with the invoice printing. When it's time to print an invoice, we can pull out the print statements from the main code into a routine called printInvoice. Then, when we want to print, we just call printInvoice. Encapsulating each discrete idea in a function might seem like a minor or even unnecessary thing to do at the moment. But let me assure you, as we get to larger and larger programs, the ability to break up and organize our code like this is going to be critical. Remember, programming languages are meant to help people, and the main thing that abstraction does is let us control the mental complexity of any piece of code that we're dealing with at one time. We've been looking at code that's gotten no bigger than about 50 or 60 lines so far. Imagine having a program with 10,000 lines of code. There'd be no way you could possibly understand all that code at the same time. But if it's broken up into these bite-sized pieces contained in functions, it's easy enough to understand any one piece. And as we keep advancing in this course, we're going to be using functions more and more to separate concepts in code. Let's go a little bit deeper into functions. Remember that functions are able to return values. For instance, the input function returns whatever the person typed in. To return a value for a function, we just include a line that says return something. Take a look at this function, which gets a person's name as a string. It gets the user's first name, then last name, then combines them with the space in between. And it returns that combined name. When we call this function, we can assign the value it returns to a variable, like you see here. Let's try a variation on this. Starting from the code we had, try making a small modification so that it returns in a last name, first name format. Here's what that would look like. We just changed the way we formed the string so that it was last plus comma plus first. We could have even just returned that string right as we made it. Notice that we just returned the combined name directly without putting it in another variable. Let's practice this a bit. Maybe you have a number game, and you need to ask a person to guess a number. How might we write a routine that asks someone for their guess and returns that value? Let's call the routine getGuess. Well, here's one way we could write it. We have a definition, def getGuess parentheses colon. Then, indented from there, we have the body, which in this case is just 2 lines of code. In the first line, we get the guess from the user. In the second, we return that guess. Okay, that's a pretty simple routine. Sometimes, we might want to return more than one variable. This example has us reading in the first and last name, and rather than returning one single combined string, we return 2 strings. Notice that in the function definition, when we return 2 values. When we call the function, we need to provide 2 values for these to be stored into. In this case, the first string returned goes into user first, the second string returned goes into user last. Now, as an aside, let me briefly open the black box about what it means to return multiple variables. This is not allowed in every other language, and technically Python is actually only returning one value. What's getting returned is a tuple. Remember that a tuple can be written as a list of values separated by commas inside of parentheses. In this example, we create a tuple with 3 values, corresponding to the first, middle, and last name for someone. We can get values from a tuple by assigning to a comma-separated list, like you see here, where first, middle, and last get the elements from the tuple. We can print the variables we were assigned, obviously. Or we can access an individual element of a tuple using brackets, just like we did for lists. So, when we're returning multiple values, we're actually returning a single tuple that contains those values. And then, when we assign that value, we're assigning the tuple. So, if we assign the function output to a single variable, like in this case to the variable name, that variable will actually be a tuple. And if we assign to multiple variables, what we're doing is taking the tuple that we got back and then assigning the elements of the tuple to those variables. Either way is acceptable. Say you want to create a function that asks a user to enter a birthday as a month, day, and year, and then returns that date from the function. Let's call the function getBirthday. How might we write this function, and how would we call that function? Okay, think about this as a tuple. After our function header, we can have a body in which we ask the user for the 3 pieces of information. Then we can return those 3 items as a tuple. A call to this function could take a single result, which will be the tuple itself, or we could assign the result to 3 different elements, the month, day, and year. Now, let's look at how to give input to functions. This is the information that we put inside the parentheses when we call a function. We call this information the parameters of the function. But how do we actually use this? We take in parameters by listing them in the function header, like you see here. In the function definition, we put inside the parentheses the name of the function is going to use for the parameter. In this case, we have a function that's going to sum up the numbers from 1 to whatever value is passed in as a parameter. We name that parameter x in this case. When we call the function, like you see below, we put in whatever particular value we want the parameter to take, which in this case is 100. Oh, suppose we remember a more compact formula for summing up positive integers from 1 to x. Notice that we could replace the inner workings of the function with a simpler formula. It doesn't change anything as far as the code calling the function is concerned. In a sense, that change to the inner workings of the getSum function is hidden from the code calling the function. The getSum function is a black box as far as the main code is concerned. It just knows that it passes in a number and it gets out the sum. Let's create a similar function for multiplication. How about we write a function to compute factorials, 1 times 2 times 3 and so on. We'll pass in a number and then return that number's factorial. The factorial of n is the product of all the numbers from 1 to n. So how might we write this function? We would start out with a function definition. We'd write def factorial parentheses, and then inside the parentheses, we'd put the name of the variable we want to use for the parameter that we want passed in. In this case, it's just a number, so we'll call it n. In the body of the function, we set the product to 1 initially, and then we loop through all the numbers up to and including n. Notice that, like the summation, we have to set the range to n plus 1, since we want to include n in the numbers we use. Each iteration of that loop will multiply the index by the product. And finally, we return the product. Somewhere else in the code, then, we can call the factorial function, passing in the number we want to compute the factorial of. Now, we can actually have more than one parameter passed in if we'd like. In this case, we're going to sum up numbers in some range. We'll create a function, getRangeSum, that takes in two parameters. We'll call the first parameter a and the second one b. Notice that they're separated by a comma. When calling the function, we also have to pass in two parameters. The example shows a couple of examples. Again, the function getSum should look like a black box from the outside. So, if we wanted to change the interior of the function, we could do so, such as if we were using the summation formula. Notice that there's no change whatsoever to the code that's calling the function. The part of code calling the function could be completely oblivious to what's going on inside. Or, here's another implementation, in which our current function makes use of the previous one. We can get the range sum by computing the sum from 1 to the ending number, and then subtracting the sum from 1 to just before the starting number. We can pick whichever implementation we like best when writing the getRangeSum function. And from the perspective of the code calling it, not a thing has changed. That last example, by the way, might give some sense of how abstraction can help. We defined one function in terms of another function. When we write more complex programs, we'll often have a sort of function hierarchy, where one function calls some others, and each of those calls others, etc. So any one function gets to ignore the stuff happening above or below it in that hierarchy. Now, although abstraction does have many wonderful virtues, there are a few potential downsides. One downside might be that you could use a function more efficiently if you knew how it worked. So, when people need to squeeze every last drop of efficiency out of a program, they'll sometimes peek behind the veil of abstraction. But those cases are relatively rare. To a surprising degree, it's better to make use of abstraction when you can. Let me give you a story. Early in my undergraduate years, I was working one summer as a part of a medium energy physics experiment at a collider. Now that sounds more impressive than it actually was, but one of the cool things I got to do was sit in on group meetings and hear about what everyone was working on. There was one group of researchers that was focused on improving the rate of data acquisition in the experiment. They had written some code in a higher level language, and I think it was C, but it ran slower than they wanted. And they became convinced that the problem was inefficiency due to the abstraction of using a higher level programming language. Well, for a good chunk of the summer, they were focused on rewriting some of that code at a lower level, assembly language, so that they could make use of the features of the processor and the memory and maximize the performance of the code. Now these were really smart people who knew what they were doing. Shortly before I left, they finished the code, and guess what? It ran slower than the higher level code had. The high-level compiler had actually produced more optimal code than their careful attempt to remove the layers of abstraction. Now, there are several lessons that could be learned here, but the thing I want you to understand is that not only you, but also every other programmer, are almost always going to be better off using abstraction to make your code conceptually simpler. Okay, there's a second, more serious downside that can occur with abstraction. And this is a pitfall that we do need to be especially mindful of when programming. Occasionally, functions will have what are called side effects. And yeah, that's the technical term. The problem here is that in the process of doing the main thing that it's supposed to do, the thing that it's advertised to do, the function also does something else. Sometimes the side effect is something that the person writing the function thought would be harmless, and thus doesn't even advertise. Sometimes this is a bug, some action that the programmer never meant the function to perform. Usually these side effects will go unnoticed, at least for a while, but eventually they can cause serious problems when someone doesn't realize that they're going to be there. Let me show you one example to illustrate. Say we've created a function, SumList, that will take in a list and sum up all the values in the list. It then returns the sum. The way we wrote this function is to go through the list and add the previous value to the current value. So, every element of the list ends up having the sum of all the elements up to that point. And finally, we just return the final value in that list. Now, this routine actually works for what it was intended to do. It does return the sum of all the elements in the list. If we just call the function and output the result, it looks just fine. But little did we know that in the process, it changed the values in the list. Yikes. If we look at the list after calling, it's totally different than beforehand. That would be considered a side effect. The routine ended up doing something that it wasn't supposed to do. Now, speaking of what functions are supposed to do, there's one very helpful practice I want to mention, and that has to do with documenting functions. It's helpful to provide documentation for functions right up near where they're first defined, and there is a standard way to do it. The documentation should say, concisely and specifically, what the function does. There's even a special syntax used to provide these comments for a function, and it's called a docstring. A docstring begins and ends with a triple set of quotation marks. You might remember that triple quotation marks are how we create a string that can include new lines, thus spanning multiple lines. The string should come right after the function header. In this case, we have a function named greet that will take in a name as a parameter and will print hello name for whatever name is passed in. So, we can create a docstring afterward with 3 double quotes saying print a greeting, hello name. Docstrings are a lot like comments in that they don't actually compute anything, but they have a second advantage. If you use the command help for any function, passing in the function name as a parameter, you'll get information about the function, including its docstring. So, in our example of the greet function, when we have the command help greet, we'll get information about the greet function, including the docstring that describes what it does. Now, let me remind you of some of the built-in functions that we've already been using in Python. We've used print and input, each of which takes a string that will be printed on the screen, and input also returns a value. We've used the int, float, and str commands to convert between strings and number types, and each of these are functions. We've used open to open files, and we've used len to find the length of a list. We've used range to get a set of values to look at within our loops. There are a variety of other useful functions built into Python, such as slice, list, and tuple, and we'll introduce more as we continue through the course. As a couple of examples, the sum function takes in a list as a parameter. It sums up all the elements of the list and returns that sum. So if we pass in a list with elements 1, 2, 3, 4, and 5, we'll get the value 15 returned. Now, we've seen ways to write our own sum routines, and there are times that we'll have complex data that we'll still want to manage that process ourselves. But for simple cases where we just want to add up a bunch of values, the sum function works great. Similarly, there are functions min and max that will return the minimum and maximum of a list. We can pass in a list in any order, and the functions will return a minimum and maximum. There are also functions called methods that are a part of objects, as we'll discuss later. You've already seen these briefly. They're the functions that come after a variable name and a period, as in the file.close function. And, besides all the built-in functions, there's a vast wealth of functions that can be called from external modules and packages, really from any Python program whatsoever. Functions provide us one of the most direct examples of abstraction in programming. Abstraction remains probably the most powerful idea in all of computer science. Look for it, aim for it. Good programmers are intensely aware of abstraction and make use of it repeatedly in different forms. The functions that we've seen here are a very direct way to put abstraction into practice. But functions have a whole lot more to them, in the way we handle parameters, for instance. In the next lecture, we'll explore parameters and functions so that we can use them more effectively in all of our programs. Let's get some practice writing a function. Try writing a function that takes in a string and a letter as parameters, and then counts how many times that letter appears in the string. Be sure you write code that lets you test your routine. Here's a hint. Remember that strings can be thought of as lists of characters. Okay, here's what your code might look like. We have a function called countChar. It takes in two parameters, the first one being the character that we're wanting to count, ch, and the second one being the string that we want to count in, test string. Inside the routine, we're going to keep a count of how many times we encounter the character, so we start with 0. We'll loop over all the characters of the string with the for loop, and for each character, we'll check whether it's equal to the one that we're searching for or not. And we'll increment count each time we find a match. Notice that we return count at the end. That's a pretty basic routine, but it illustrates the main aspects of a function. There are input parameters passed in, and a value is returned. And just as importantly, we've separated a single conceptual idea, counting characters in a string, into its own section of code.